All right, so we'll get started here.
Sleeping toilet.
Do one. Okay, so I've got Zoom up and running. I've got the slides kind of on my ready to go. Mention a couple things related to Stata before we jump into it today. Those of you who are having some issues at the end of last class where you weren't able to kind of get it to open up in a web browser. So, and that's not being on my laptop, so I can show you kind of what it end up showing you. So if I go to IU Anywhere, once I've kind of got that cloud storage, that step, it seemed like most people were able to authorize that. Okay. Go to detect Citrix Workspace. I mentioned that some of you may need to use the light version. If you use the light version, you don't need to. I think that's why it's uploaded or opening it up in a web browser for you. So if you accidentally selected the light version or trying to just do the regular version. So if I did the regular version on this device, it worked okay. If it didn't work for you, what we want to go, if you go here and you try to open up Stata and it opens it up like as another tab in the browser. First of all, you can try using different browsers and it may not default to that. So usually Chrome and Firefox are the best bets. So Safari sometimes has some issues trying to open it up in a separate browser. So if you go to this account settings, and I showed you this last class, so you can go to activate your workspace app. You can also go to change it. So if you accidentally selected the light version and it's opening up as a web browser, you may want to go to change and then detect as opposed to clicking that use light version. Also, from what I can gather from talking to the tech people and looking at a bunch of different files, sometimes it's the exact opposite problem. Sometimes your device needs the light version and you've just selected to detect Citrix Workspace. So try both of them. And the way that you can try both is to just hit detect, or if you do hit this light version, now I'm going to have some issues if I try to open up Stata, I believe. We'll see. Maybe both of them will work on this device. So see, it's trying to open it up as what in my web browser now. I don't want that, so I'm going to stop it. I'm going to go back to account settings. I don't want to use the light version. I want to detect that workspace. Now when I go and try to open that program up, we'll wait for a little bit, but it should open it up now, kind of not in my web browser, but like what looks like is a separate. I've got the spinning wheel on my other screen here, so I'll have to drag it over as soon as it pops up.
Yeah.
We're waiting. I didn't open this ahead of time because I wanted to kind of show you the steps here. There it goes, right? Now I've kind of got this open up what looks like a program, okay? So switching between that light version or not might resolve a lot of the issues that we were having last class. If you're still having some issues, maybe we can hang around and talk a little bit after last class. Got a couple other things. I've got some help files that we can try to work through this. So if I go to Canvas, I put up kind of this Stata issues resolution document. It kind of has some steps, that's kind of what I just talked through, changing it to the light version or switching it to the light version, depending on what device you're using and what issues it's having. I also, oops, where was it at? It was in that file. Let's go to the home page. It also may have kind of trying to open up this file type. So you might have to go through these steps of like going to your default apps. So I can kind of try to help you with that. Or if you want to try to work on your own, that's fine. So that help document is there. I also put up, and this was also, we're waiting. It's a little bit slow in here. Well, once this downloads, or once this uploads, it doesn't like it. Why isn't it? Right, downloading it, opening it up. So here I kind of put some bolded steps to kind of switching the light version. Also, maybe a little bit easier kind of follow steps of changing your file extension. I also put up the link that kind of has help getting Citrix Workspace working on your device. Okay. So if you're still, how many of you are still having issues getting Stata to open up and what looks like this? Okay. So try kind of those that switching to the light version or switching off of the light version. If that doesn't correct it, kind of talk with somebody after class or troubleshoot this before we really start using Stata a lot today. If you're not able to get it open today, you can copy everything down that I'm doing as opposed to in Stata in a Word document, right? You kind of just type it out, and I'll explain that when we kind of get to the portion of today's class where we'll use Stata. But as a reminder, even once you can get to this step, you're going to have to make sure that all the files, when you go to Canvas and download them, they will initially download into like your downloads folder, but you're going to have to drag and drop them or change the default, although I don't think you probably want to do that. You're going to drag and drop them from your downloads folder onto your OneDrive. It can only open up files from your OneDrive. Yeah.
Is it okay if we use the version that opened the browser?
So if it's working correctly for you, that should be fine. I know for a lot of people, when it's opening up in the browser, they're having issues opening files up from their OneDrive. So that's probably that you might run into an error at that point if that's how you're using it. Any other questions for you starting the material here? Okay. Also, this might be something, if you're still running into issues and we can't resolve them after class today, maybe stopping by my office hours. I'll actually be around a lot tomorrow. So maybe stopping by tomorrow in my office, I can try to give you some one-on-one help. Like I said, I am not like a tech person. I know a little bit, it's not enough to be dangerous, but with so many different devices, it's hard to really troubleshoot, give a general answer because it's probably going to be specific to what type of device you have. So where did we leave off? Really, I think I know how this is set up. There we go. So we started talking about just different types of data sets. So just some basic review. I'll go through this probably pretty quickly because you all should have taken 370 or an equivalent, right? So you have some basic statistics behind you. If we're thinking about our population data sets, we're typically going to denote this with a capital N as the number of observations that are in that population data set. This should hopefully sound familiar. How do we denote sample size number of observations? Everybody remembers this from stats? Capital N's population size, lowercase n is sample size, okay? So, we can think about this would be like if I had a data set with every single US citizen. That'd be awesome to have a data set that big. But maybe I've just got like a country level data set. So I have every single country, I have like their GDP. I think that was one of the data sets that we had looked at last class, right? So here, kind of my population size would just be the number of countries in my data set. And then, you go through a list of other examples. If I had to have automotive firms, so I have firm level data. I might have school level data. It would be the number of firms or the number of schools is that population size. We're also going to use random variables. So sometimes we'll have observations where each observation is kind of representing an individual, but we're also going to talk about sometimes we have a variable, we don't know what the outcome is going to be, but there's different probabilities associated with seeing different values, okay? So, for example, if I'm thinking about the average test score of an Indiana school, I know that it's probably, and I'm thinking test score, I'm thinking like I-step scores, I know kind of the range it's going to be in between, I know the possible values, and I know that if I selected a school at random, they're more likely to have a value that's probably closer to the mean than they are a value that's very far above the mean. And there's going to be different probabilities associated with seeing those different values. So that's our random variable we're thinking about. If I've got a variable, I'm selecting one of these observations at random, what's the probability that it takes on a certain value? Okay. So we're thinking about these random variables. We're thinking about just a variable in general. We typically want to talk about and think about its distribution. Okay, so all we're going to do if we have this random variable where different outcomes have different probabilities associated with them is we're going to take that value. So maybe an I-step score of, now I forget what I-step scores are. Let's see, a math score of 460, right? So 460, what's the probability that we see 460? Plot that on a graph, right? Go to 460 on the x-axis, y-axis would be the probability associated with seeing that. And then we would then want to do that for every single possible math score. Right now here, obviously it's a little bit more continuous. I've kind of forced the data here to be like in bins, right? So the probability of seeing like a score in between, about 330 to 335 looks like it's about just under 1% or a probability of just under 0.01. And I think about what's the probability I see a score, looks like here's like 355 to 365. If I just selected one student at random from that data set, well, that probability is about 0.04 or roughly 4%. So one thing that I'll do a lot of in this class, like we can convert between percentages and probabilities. Hopefully this is very easy for you guys at this point, right? If I have a probability of 0.23, that is what percent? 23%, right? I'm just multiplying by 100 and moving the decimal. So I might, in my speech, kind of go back and forth, right? I might say probability and accidentally tell you the percentage, right? Or vice versa, but right, it's a very seamless transition between those two. So this would be like what we would call a discrete distribution, because I've forced observations to kind of be in these bins, right? If I just allowed for it to be any possible math score, I allow it to be more continuous, right? I could see any value from, I guess, probably technically 0, you get on this test up to whatever the maximum score is. We're going to end up with a more continuous distribution. Right? Now, when we have a continuous distribution, this gets a little bit tricky. What's the probability of seeing any one specific value if it's truly continuous? If I could see any score 360.12597, what's the probability? How many possible values would there be if I could see it out to any decimal? Technically, it would be infinite. So if there's infinite possible values, 1 over infinity is in the limit 0. So when you have a truly continuous distribution, the probability of any one value is 0, but we can find, it kind of seems counterintuitive, but the probability it's in between a range of values will be some positive value. And what we're really doing there, we would be like taking the values we're interested in, integrating this function, finding the area under the curve. We're not going to be doing the integration, but that's essentially where those probabilities are coming from. So just some other kind of review of some things hopefully you've seen before. We'll be using this summation sign quite a bit throughout the semester. So all this summation sign means, right, this Greek letter sigma, is start. I is kind of representing the number of observations you're looking at. So this says start at the first observation in that data set and go to the 5th. Now, generally, when we're writing this for a whole data set, we would start at 1 and go to capital N, the very last observation of the data set, right? But if I was to just add up the number 2, once, twice, 3 times, 4 times, stop at 5, it would really be like taking 2 plus 2 plus 2 plus 2 plus 2. This summation of 2 going from 1 to 5 would just be 10. Now, we're generally going to use this to kind of calculate means, things like that, not as like just adding up a constant. So generally, we're going to say, okay, take this random variable y. So this was like the math score. Go to the very first student, this variable y, which was math score, for that first student, take that number. Then go to the second student, add to that their math score. Go to the third student, add to that their math score, all the way to the very last student in this data set. Now, if I was wanting to calculate a mean, how do I find the average of a set of numbers? I add them up and do what? Population mean, just divide by. If I told you to find the average of 10 values, what would you do?
Divide by 10.
Yeah, hopefully this is not wild, like new information to any of you, right? So if I'm trying to find the mean from this data set of this variable, if I add up every single value for this variable, I would then divide by not 10. The number of numbers I'm going to have in my data set is capital N, right? So I would add up every single observation's value for that variable and then divide by the number of observations I have. Okay? So it's just kind of a fancy way of, it's just a fancy mean. Right? So I already mentioned the mean, kind of leading you, right? Leading a horse to water there, with we can take that summation sign, add up the value of every person's test score, divide by the number of people that are in the data set. That should give us the mean or the average or the expected value of that variable. All of those kind of terms mean the same thing, right? Average, mean. Technically, expected value is when we have probabilities associated with different values. So that could be for a non-continuous or for a discrete variable, but really all of those kind of terms are interchangeable. Now, the way that we'll write the mean, just kind of in notation, because we'll use it a lot throughout the semester, is for a population, we're going to write this as capital mu. So this is Greek lettering. Anytime you have population data, you're going to use a symbol that's a Greek letter. So most of them, almost all the time. That's a pretty good like default. Okay. So here I've got the mean of this random variable y, right? And I've calculated by how we just talked about. Now, some other measures of central tendency. You got the slide, so you can even guess a little bit ahead of time, help this go a little bit smoother. Median, right? So we've got multiple measures of central tendency, and I'll come back to this one. One is the mean, right? But what is the mean really influenced by? Yeah.
Outliers.
Really large or really small values, right? So I always use the example like in grading. If you get a 0 on something, why does that matter so much? It's extremely low value. It's going to pull your average grade down a lot. Now with the median, so if I think about getting this so you guys can see it. Okay. So So let's say I had a set of numbers and I wanted to calculate the mean, right? So I've got what? We'll do 1 + 2 + 3 + 4. Divide by, I've got 4 numbers. So this is going to be what? 10/4. I have a mean of 2.5. Okay. If I want to calculate the median, so this is capital M subscript D, what I would do is I would essentially take those numbers that I have and I would find the value such that there will be 50% of my numbers on one side and 50% on the other. Or in terms of data, the value that would give me 50% of the observations above it and 50% below it. So in this example, if I do that, well, I'm left with 2 numbers. It's kind of hard with an even number data set. Do you remember, how do you find the median if you have an even number data set?
Take the middle, divide by 2.
I would take the average of those middle 2, those last 2 values. Now, if I had 100 numbers, I do the same process. I just start crossing them off all the way till I get to the very last 2 in the middle. So here, what would my median be? Exactly the same as the mean. We'll talk a little bit later, but this would be a data set. It's a very interesting data set that is symmetric. Anytime the mean is the same as the median, we have a symmetric data set. Okay. Now, what if instead the set of numbers I had was this? Okay. So if I find the average here,/4. If I'm doing math in my head correct, so I should have a mean of 10. Notice that one extremely large value, even though 75% of the data set is exactly the same, with small data sets, really large values will do what? Increase the mean a lot. Okay. Now, if I was looking at the median for this data set, notice an extremely large value still just gets crossed off once, right? It's still just one observation above or below the middle of that data set. So what's my median here? Still 2.5. So our outliers or our extremely large or small values aren't going to influence our median. They're going to greatly influence our mean. Okay. And this is just a kind of toy example to really show us that that's the case. Okay. Just thinking about this in terms of distribution to be a little bit more technically correct. Those are just small data sets. So if I had any random variable y, and I was kind of graphing the probability that y value takes on a specific value, and I had continuous distribution that looks something like this. I try to draw it symmetric. It looks like I got a little bit off with my tail here. So this would be an example where my mean is the same as my median. If I instead had basically the same values in my data set, but then the higher values really, really large, what's that going to do to my mean and my median? The mean is going to go this way. What's going to happen to my median if I still have the same number of observations on each side here? All this median 2, right? It would stay the same, right? Now, is this likely going to be the case where like everything below the median stays the same and everything on the right-hand side increases? Probably not, right? There's probably going to be extreme values on either side, but this is just one way of kind of highlighting what we just did with those small data sets, just in terms of a continuous distribution. Okay. Questions? Okay. Let me think if there's anything I want to say here. I think I'm jumping the gun a little bit in terms of where this is at in the slides, but we're going to have to talk about it at some point, so that's okay. Anytime I have a mean, and let's say it's greater than my median. But what does that mean? It means that I've got the mean is larger than my median. I must have very large, extremely large values in that data set that are pulling the mean up, but not impacting the median as much. So anytime this is the relationship between the mean and the median, we're going to talk about different types of skew that a variable or that a distribution has. So if the mean is to the right of the median, right, it's greater than, we would say this has right skew, or this is right skew, a right skewed variable or right skewed data. Anytime we've got the mean being less than the median, this must mean we have really extremely small values, right? It's pulling the mean to the left of the median, so we've got left skewed data. And then just to be complete, if they're exactly the same, we said this is what? Symmetric, right? Okay. Focus this one more time. It's looking a little. Okay. Is this ringing a bell? Sounding a little bit familiar, hopefully. Okay, so like I said, it's a lot of review today, but we're also going to see how we do this in this data. So we'll get a little bit of practice here. Now I'm going to have to get enough practice to use. There we go. So we didn't talk about the mode. It's not the most interesting. We won't do much with it throughout the whole semester. Does anyone remember what the mode is? It's just the value that happens the most often. All right. So if I'm looking at a distribution here, what would the mode be? It'd be the value that has the highest probability, right? It's the one that shows up the most often. So wherever the peak of that distribution is, that's going to be our mode, right? That's the value that happens most often. Now I just kind of skipped over this guy. So if we do have a discrete random variable, and I'll work through an example here of this today. What we're going to do, we can't simply add up all the value. In my example, I had 1, 2, 3, 4, and 4. Or those are the 4 numbers I had. I was treating them all evenly. But if 1 was more likely for me to see in the data set than 2, how they have different probabilities associated with them, what I actually need to do to find the mean is take each one of those values, multiply it by the probability I see that value, then add them all up. Now, I don't have to divide by anything because technically the number of values I have, if I'm using probabilities, what would the probabilities always add up to? If I've looked at every single possible outcome, the probabilities should add up to 1. Okay? So if I'm dividing by, now I don't have a set of numbers, I have probabilities associated with these numbers. Instead of dividing by n, I divide by the sum of the probabilities. The sum of the probabilities is always 1. So we don't usually write that in there. Technically, there should be a denominator with that, but it's always going to be 1, so we don't write it in there. So we have measures of central tendency. We also have kind of measures of dispersion. So the first one is the variance. So once again, population variance, we'll kind of use this Greek letter sigma, like sigma squared. And how we're going to calculate a variance? Well, to calculate the variance, we first need the mean. That's why we had to talk about it first. All we're going to do is go through every observation in the data set, take that observation's value for this variable we're interested in finding the variance of, y, subtract the mean. We call that the deviation from the mean. We then square that deviation, do that for every single observation, starting with the first, going to the last, add them all up. So we add up every observation's deviation from the mean squared. And then just like the mean, we divide by the total population or the total number of observations in our data set. Okay. So once again, this hopefully shouldn't be that new information really. We could do the same thing if we're doing it for a discrete random variable. We would just be adding up all the deviations from the mean squared, but multiplying by their associated probability. Okay. So here we've got, let's see if this works so I don't have to keep walking. There we go, walk back and forth. The standard deviation, which notice the notation looks very similar to the variance, it's just not squared. So if I have the variance, how would I find my standard deviation? Yeah, just take the square root, right? So we calculate, in order to have the standard deviation, technically you're having to calculate the variance and then just additional step, we take the square root. And we'll kind of see why the standard deviation is usually a little bit more useful in some of the other things that we're going to do statistically. Okay. So we're not just like doing math for the sake of doing math. The standard deviation, it gives us better interpretations, and we start thinking about like the standard normal distribution, or sorry, the normal distribution, it starts to make a little more sense why we want this instead of the variance. So if I had a data set that looked like this, so instead of kind of my nice observations, I've got probabilities associated with seeing a different number y here. Okay. I think I used to have this like as the number of wins a football team can expect. I probably should update this especially for IU because hopefully numbers at the bottom have higher probabilities this year, right? So if this was like the number of wins I'm going to get in the season, so these are the different possible values I could see 0 through 12. Now each one has a different probability associated with it. Now what's kind of nice about this data set, if I was going to find the mean here, I should go through every single value, multiply it by the probability it occurs, add them all up. Well, anytime the probability is 0, do I really need to be concerned with that value? No, anything times 0 is 0. So what I would do is just go through 0 times 0. I don't have to worry about that. Add that to 1 times 0.06. Add to that 2 times 0.03. Add to that 3 times 0.2, right? Do that for every single possible value for y. Once I've added them all up, that would give me my mean. So sometimes I'll jump into Excel here just to be my calculator instead of doing all this math by hand. Oh, I'll actually open up, where's that? Oh, here it is. Open up this example so I can have Excel for us here in the class. We won't use this yet, so I'm just going to use this to be my calculator. So I've got all my values here. How can I do this pretty quickly in Excel? I would just take the value for y, multiply that by the probability I see that value. Now I can copy this down. Does that for every single one. Now, once I've got format this to be the same, so nice and easy for us. So this is essentially y times the probability y is equal to a specific value, right? So once I've done that, need to then add up all those values. So I get a mean here of about 5.12. And we can kind of check ourselves, like the probability, the values that had the highest probabilities were some of the ones kind of in the middle here. So they should be having more influence over that mean than some of the extremely low values that had low probabilities. And then I think the extremely high values, a lot of those had 0 probability. So they really shouldn't be influencing the mean at all. Now, once I have this mean, how am I going to find the variance of this discrete random variable? I'm going to go through, take every single value and do what? So I need to find the deviation of this value from, just said a little while ago, the mean. So I'll take this value, subtract the mean, then do what? Square it, go to the next observation, take its value, subtract, sorry, I forgot a step. Square it, then multiply it by its associated probability. Then go to the next value, 1, subtract the mean, square it, multiply it by the probability I see that deviation from the mean, or that I see 1. Then go to the next value, 2 minus the mean, squared, times the probability I see 2. Go through and do that for every single value and then add them all up, and that should give me the variance of this discrete random variable. So I could actually create another column where I take y minus the mean squared times the probability that it equals that specific value. So I'll take y value minus the mean, square it, right? And then just so it's easier to see here, take the probability that we see that deviation from the mean, oops, and multiply it by that deviation squared. Now, when I copy this down, we're not whizzes in Excel. I don't want that cell that the mean is in to ever change, so I'm going to freeze it with $signs. Now, I do this for every single observation. Notice the values that had 0 probabilities. Well, when I multiplied that deviation from the mean by 0, it ends up being 0. So now to find my variance, I'm just going to add up all those deviations from the mean squared times their associated probabilities. And now I've got my variance is about 5.4. Now you can do this by hand. I'm using Excel to make it a little bit quicker to kind of save class time, so I'm not writing out every single one of these 12 values. But hopefully this looks also like something you've seen in 370. Any questions over this? We can jump back. Okay, where are we at in time here? That's 45 minutes. So I think what I'm going to do here. There we go. So that was kind of our mean and variance example, kind of talking through that a little bit. We talked about skewness. I put up the actual formula. I'm never going to give you an example where you have to calculate it by hand. In terms of when we talk about skewness, we really just care about that relationship of the median to the mean. And also once we get to Stata, it's going to be able to report the skewness to us. It's going to calculate this behind the scenes. So we're not going to worry about kind of doing this by hand. Okay? So I put the formula up there, but really all we're going to use for the sake of this class is that relationship of the mean to the median. kind of concerned with whether or not skewness is positive or kind of right skew or left skew. Okay? So technically, right skew is positive, left skew is negative. Depends on who you talk to, whether or not they'll use that. Probably more like data scientists, people will use positive, negative skew. Economists tend to say right and left. I usually default to right and left. So I apologize for that if you learned it the other way, but really positive is right skew, negative is left skew. And then we had our symmetrical distribution as well. I'm just mentioning this to be complete. We aren't really going to do much with this in this class, but kurtosis is like, when you notice we're going from mean to variance to skewness, we're going from to the power of 1, 2, 3, and now 4. Kurtosis is going to measure something about what we call like the fatness of these tails, right? So even here, I've got symmetric distributions, right? They're all symmetric, but they have different kind of heights, right? So this distribution is much more likely I see values near the mean. This distribution, it's a lot less likely see things near the mean, much more likely I see things that are further. Right? It's just a measure of how fat those tails are, right? How many outliers, kind of a measure of somewhat of the outliers that I've got. So we are then going to transition to data here. We'll open up that review of statistics fall 2025. So I've taken Canvas files, downloaded them, and I dragged them onto my OneDrive, okay? So that's why I'm not using the actual program on my laptop during class, because I want to do everything that you guys are going to have to do, which is to use this web-based version of it. Okay? So I've got this in my OneDrive. I'm going to open up that do file, right? So remember, our .dta files, those are the actual data files we're opening up. Here, I'm opening up a do file. All that is where I'm saving the code that I'm going to be putting into Stata, okay? So I'll kind of walk really slow through this today. I don't know exactly how far we'll get, but there's a lot here, and you might be like, "Oh my God, like, what is all this?" Right? We'll walk through it line by line. I try to, in all the do files I give you, put lines of text here. So the way that this is going to work is in my do file, I will highlight the code that I want to run. Now, there's some nice user interface stuff you can do. So here, this line of code is just opening up that state cigarette tax file that I put on Canvas, right? Now, it's not in Stata format. It's a .csv. So I need to import it. I can't just simply open it up. If I try to go to, let me move this so I can move back and forth a little bit easier between my do file here. So if I'm in the actual program, not in my do file, if I try to go file open, and I try to open up that state cigarette tax, oh, nope, that's the wrong one. Sorry. So if I go to file open, in fact, it isn't showing that I have that CSV file in there. It's only going to be showing me my .dta files or my do files. So it'll look like the file's not there. And you're like, well, I know I put it onto my OneDrive. Why isn't it allowing me to open it up? Because it can't actually open up any other file other than these .dta or these Stata dataset files. So what we're going to have to do is, instead of going to file open, you could go to file import. We're trying to open up, this was a CSV file. Notice you can open up a lot of different types of formatted data sets. Here we'll go to CSV. Now, when I go to the file, now I see, oh yeah, it is actually it defaulted to that folder on my OneDrive. So if it wasn't, I just go find where that CSV file was. Hit open. It shows me what the data is going to look like once it imports it. Hit OK. Now this is where, if I had a data set opened up, since I accidentally opened the other data set, this is a good point. It's going to be like, wait, if I can only have one data set open at a time. Okay. So in order to open this one or import this data, I have to get rid of the old one. I'm okay with that because this is the one I actually want. Now, notice anytime I do something from the interface, right, like file and import, it tells me what the code was in order to do that. So if you like to use the kind of interface up here, you can do that, right? You can file import. However, if I exit it out, all of this goes away, it doesn't get saved. That's why we have the do file. So sometimes what I'll do, if I don't want to type all this out, is I'll use the interface. I'll go to file, import the data. But then what I do is, in case I ever want to go back, I don't want to have to keep going through these steps. I'll highlight it, copy it. Well, it doesn't look like I pasted it. Hold on. It's the exact same thing. So we go. I'll paste it here. Now, because I had the window small, I need to like make sure I get rid of that. So you'll kind of notice. No, out here. Like it didn't put it over here. It kind of had to drop it to a separate line. So this little like arrow is like saying this is an extenuation, right? So this isn't actually part of the code, right? It's because it didn't have enough screen space to display it to me. So that's where that line of code came from, was just going to the file import and importing that CSV file. Now, we're going to fall behind quick if we don't ask questions. So are there any questions, anything about that? So generally, what's good practice, first of all, this comma clear should always be in there. So if you start out without any data, it won't ask you that question about like getting rid of the old data, and it might only give you this. If I try to run this, so I highlight the code I want to run, I then hit this little execute button up here. Oh, gives me an error. Why? Because the old data that it's trying to kick out, I would lose that. So what I need to do is tell it, I want to import this data. And if there is any other data sets open, comma, I just want to clear them out. So that should kind of be added in there to make sure now. Oops. Okay, now it's getting rid of the old data and uploading or importing that CSV file. Now, what you'll also notice is anytime I use these double backslashes, so this is where I'm going to put comments into the do file. It's also going to be helpful to you to like remind yourself of things if you like start and stop the next like the first problem set. It doesn't, it shows that on the screen, but it's not code. That double backslash tells it that this is just text in my do file. So notice, even though I had that highlighted when I ran the code, it doesn't screw up anything. It just Stata automatically knows, oh, there's a double backslash in front of it. That's just text. Okay. Now, and I already showed that to you kind of, if we don't use the clear command, we're going to have some issues. So I need to make sure I have that clear command. So just some very basic things I could do. Let's say I open up this data and I want to change some things. So like if I looked at the data, so we go to that magnifying glass, just kind of the data browser, open it up on my other screen. But so here's my variables. Here's the variable names. And here's my 50. Well, actually, I have more than 50. I have more than time periods. I've got a bunch of observations, right? So some of these, sometimes the variable names will kind of upload like is really weird. And you're like, I'm not going to remember what location DESC means. That's just state, right? So sometimes what might be helpful is to rename variables, so they're not as long when you're typing them out, but also so that it reminds you of like, what is this actual variable? So the location ABBR, I'm just going to call that, rename that to be state. So I put what the original variable name was, location ABBR, and I'm just going to rename that to be state. So notice when I run this line of code, so it ran that line of code for me. And then in the actual data, notice it's changed that variable name to say state. And then I might want to rename another variable, that location DESC. I want to rename that state name. So I run that line of code, it changed that. Now, if at this point I was to exit out, right, it's not going to save this. I mean, usually any data set I give you, you don't want to start overriding the original data, right? So if I'm changing things here, I probably want to save it as like my own data set, okay? Now, it's a CSV. I don't want to save it as a CSV. I want to save it as a .dta file. So once again, you could go up here, go up here to the program, go File, Save, right? And type in whatever you want to call it, right? I think here I just called it state sigtax, right? Now, automatically it sets it to be a .dta. So I've imported that CSV file. I'm now going to save it, but it's saving as a Stata data file. So now I've got this saved. Okay. Now, since I had already saved this ahead of time, what will happen is if I try to do this it automatically, if I do it from the interface, identified that like I had to replace, there was already a file named that. So it put in that comma replace for me. If I didn't, the first time I save it, I only have to use the save command, right? I can highlight this, right? So if I try to do that now, it's gonna give me an error because it doesn't have that replace. It's gonna, has that data set already there, so it can't save something with the same name. So that comma replace should always, right, out of like good practice, we should always default to putting that replace at the end of the save. And then now it works okay. And then this is a way, if you save it as your own .dta file, as you start to work on these problem sets, you can save your work along the way, right? You can stop working on it and then kind of come back to wherever you left off, right? Just reopening the last time you saved the data set, and it'll have all your old changes. Now, that doesn't mean you always have to like save it. In fact, I don't often save this a lot because, well, I'll hold off on telling you that in a second. So this would be how you save it, right? Let me think of anything else I want to say here. Oh, so you can go through, use this like system of using the interface, like file, importing, opening up files, saving them. What you can also do, and I will do this a lot in the do files, you don't have to do this. You can always like put whatever the state of code spits out at you, use interface, you can always use like the full file path. But just because like it's really long and it makes it a little bit easier when you're working on it, if you want to keep like opening the same data set, what I will do is do something called setting a path, right? And I actually usually put this line of code at the very top of every one of my do files, okay? So what this will do is it says create this global like variable behind the scenes called path, right? It's not a variable in the data set, it's like something that's existing in the program. And this global variable path, I always want it just to be this text, which is the file path that I'm using. So notice mine is so yours should be this will be your OneDrive essentially. I think for some of you, this will be like a longer thing where it's like OneDrive, IU, your username. For me, it's for whatever reason, when I'm signed in, I think it's because I'm an instructor, it's just so this might look a little bit different, but whatever that file path that it gave me. So notice here, this was what the actual output was, right? So I'm going to select it. I only want to select the file path, right? Not the actual name. I just want, where is it being saved? Where is it being opened from? I can copy it. So if I didn't already have this in here, I would then paste what I copied. I need to make sure that it's in quotation marks here. But what this does, when I run this line of code, is it sets up this global path so that anytime after this, if I put a $sign and then these like squiggly brackets and whatever I called that global variable, it automatically puts in this longer line of text. So now when I go to use, and all I want to do, use is just essentially open, right? So when I open up a .dta file, that will just be use, right? That's the code that did that for me. That's the code that it spit out for us in Stata. Now you don't have to always go to file open. You can just literally type use, right? And then here's my file path. This is the file I want to open up. And then we had comma clear because we already had a data set opened up. We're going to have to clear it out. So now go and run that. It used that global path. And sure enough, it opened up that data set where we had made those changes and renamed things. Okay. All right. So just trying to get kind of familiarized with Stata here. Any questions at this point? Okay. So you'll notice as I show you almost every line of code here, I'm giving you some type of description over what it means. So like, I'm never going to make you like in class, you're not going to have to type out every single thing that I'm doing here. These do files are really meant to be, probably is helpful if you have them pulled open and kind of work along with me during class. But they're also meant to be really good help files for those problem sets. So I'll actually tomorrow get the first problem set posted so you can start trying to work on it early. It won't be due for like another 2 weeks, right? So the 2 weeks from today. But I want you to start to try to work on this, try to work on opening up some of these programs. Some of this stuff will be pretty easy that we talked about today. And then you won't be able to get very far this weekend or until next class, but after the next two classes, we should have went through enough to where you could really like do almost everything in that problem set. Okay. So just a couple other things that we might want to do. Now, this isn't always going to be the case, and if I wanted to do this, I'd probably tell you. But we have this really big data set. I just want to make it cross-sectional, and I just want to keep 1 year of the data. Okay. So one of those commands that we have in Stata is this keep command. So if I'm ever only interested in like one specific type or one specific year of this data set, if I say keep, that's telling it keep all the observations only if this conditional statement is true. So if that variable year, right? So anytime I'm typing out like these variable names, that should correspond to a variable that's in my data set. So if this variable year is equal to what, 2000, I want to keep it. So anytime we use a conditional statement, we would say if, you use parentheses, and then if you want to know if something's equal, the syntax of Stata is a double equal sign. If it's greater than or equal, greater than, and an equal sign. If it's just greater than, just a greater than sign. The equal one's the only one that's kind of weird is that you need two equal signs. Why? Just the way that the syntax is, okay? There's probably actually an explanation for it, but I mean, you know, if you've got a program, you can code it so that it could have identified one equal sign, but here we are. So keep it if it's equal to 2000. If I run that line of code, okay, it deleted almost 2,500 observations. Now, when I go look, all I've got is a data set with states from the year 2000. Now that's the data that I want to focus on. I want to start to create things like the mean, the variance, et cetera. So a quick and easy way to just get what we call descriptive statistics of the data is to use this sum function. Or you can type it out. I think the actual function, you can type out summarize, right? But I try to always give you the code that's the easiest and the shortest to type, right? So summarize or sum, right? And then what variable do I want to summarize? That state tax variable, okay? So if I go sum state tax, and I run that line of code, in the program, it'll spit out at me, okay, there's 51 observations here, which is only 50 states, so DC must be in here. If we look at the data, I'm guessing. It tells me the mean, the standard deviation, and the minimum and the maximum of that variable. So the lowest state cigarette tax was what, 0.025. The highest was 1.11. The mean was about what, 41 cents, 0.41. Okay. So very quickly, I can get the mean, standard deviation, minimum, maximum. In fact, if I use sum, and then I put after the variable name, comma, detail. Excuse me. I not only will get that same information, but I'll get a lot more. So notice it still tells me the mean, standard deviation. It now gives me the variance, the skewness, which it's positive. So I must have a right skewed data set, which should mean what? If it has a positive skew, we said that's the same as a right skew. So what should be true about the median relative to the mean? If I have right skew, that means the mean is to the right of the median. So my median should be lower than what, 0.418? Sure enough, it reports to me the percentiles. Well, what's the median? It's the 50th percentile. The value that there's 50% of the data above and below, sure enough, that median is less than the mean. So that very quickly, we can get like all these just without doing a lot of the work by hand. Like this just saves us a lot of time. In fact, oh, what's some other ones? So we can do tax revenue here. I can type. You can actually do the same thing, but for multiple variables at the same time, right? So if I wanted to summarize multiple variables, I just separate them with a space in that sum command, and I can actually get all those descriptive statistics for multiple variables. Any questions? Anything here? We're seeing at least even already how much time this could save us from calculating all those statistics. Now, one thing that we're going to want to do is eventually, we might want to start creating our own variables, okay? Now, we can get the mean and these other statistics from that sum function, but we might want to use them later on. So later, I'm going to show you, I think I've got down here, I think we'll get to it today, but we might want to standardize the variable. So we want to actually have that mean, but we want to store it somewhere. Okay? So anytime I want to create a variable, I'm going to use this EGEN command, okay? Now, sometimes I'll use the gen commands. This is kind of confusing. I'll admit that in state, especially early on. So you'll notice here, like I've got gen, and then I'm doing some type of equation to create a variable. Gen is when I just want to do basic math to create a variable. So if I wanted to do like, I just want to generate a variable and I want it to be equal to 5. I don't use egen. So if I try to do egen here, it's going to say that's what are you doing? Anytime I just want to create a variable and have math, so even if it's like equals 5 squared, blah, 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 even using different variables, I need to only use this gen command. All right. And then it should, if I look at the data, have created that variable which was taking 5 and squaring it. Now, if I want to use built-in functions in Stata, that's where I need to use egen. Okay. So here, there's already a function that calculates the mean for us. So we're going to use egen and say, I want to create this new variable, which is the state tax mean. So I use underscores a lot. You can't use spaces when you're creating like the variable name. So if you ever want there to be a space, just so it's easier to read or easier to look at, I generally use just an underscore. So create this new variable that is equal to the mean of our state tax variable. So what this should do is create for every observation this variable state tax mean and just put in the value, whatever the mean of that state tax is. So now I run that code, I look at my data. Sure enough, it's calculated that mean. We get that 0.41 and it's just stored there for every observation. So egen is when I want to use built-in functions that are in Stata. Gen is if I just want to do some type of like variable creation where I'm just using like math. Okay, just basic like for function math. Okay. I can do the same thing. It's got a built-in function for the median. It's got a built-in function for the standard deviation. Standard deviation is just SD. That's what the name of the function actually is. So I can run this line of code pretty quickly. And now I can see, okay, I've got the mean, state tax, the median, and this standard deviation, right? All stored into one variable. Okay. Now you're like, okay, well, what's the point of that? I could have just done the same thing using the sum command and looked at those values, right? But you know, that sum, when we use that sum command, that output, I can't save that, right? That goes away when I close out of the program. If I save this data set now, what is saved? That mean variable, that standard deviation variable. So I would still have those values as opposed to like having to rerun the sum command and then go back and look at it. So it kind of depends on what we're wanting to do, but that can sometimes be helpful. Now, when it's also helpful, we're going to come down here. I'm going to skip this for a second, is when we talk about standardizing variables. So do you remember when you wanted to standardize? So if you guys did like a normal distribution, when you standardized it, it turned into what? You had a table for it in stats. It was a 1-letter table. Jesus, what are they teaching in 370?
T distribution.
Yeah, T distribution or a Z table, right? That was the standard normal distribution. I want to standardize a variable, okay? I teach 370, so I know I'm teaching it. If you had me, I don't think I didn't recognize any, but okay. So how do you standardize a variable? How do you turn it into a Z score or a T value? You would take what? Take the value, subtract the. That'll be a long semester. How do you standardize a variable? You subtract the mean and you divide by the standard deviation. Okay, I will review that again. I've got some slides for this. Assuming that that would be a waste of time, but maybe I'm wrong. So you'll take the value, subtract the mean, divide by the standard deviation. So here, I want to take, instead of that state tax variable, I want to take this packs per capita. So it's the number of packs of cigarettes smoked per person in that state. So the name of the variable is packs per capita. I'm going to generate, using the egen command, the mean and the standard deviation of that variable. So I'm just going to run that code, do that for me. I now have my packs per capita, mean and standard deviation. What I'm then going to do is I'm going to use the gen command to simply create this standardized version of the variable. So I want to have packs per capita standardized, essentially turning it into a Z value. I'll take the value that I see for the observation, subtract the mean. Well, instead of like saving and typing out the number, technically I wouldn't actually be precise if I do it that way, because I'd have to round somewhere. If I create these variables, it stores it out to whatever decimal the mean stops at. So here I'm taking the value of each observations for pax per capita. I'll subtract the mean from it and divide by that standard deviation. And I'm being very precise. I'm not rounding by having, using that sum command, right? The summarize command where it just gave me the output. So here, if I run this, right? And it's created it. I go ahead and look at it. Okay, looks like it's standardized as variables. Some are positive, some are negative. So I guess this is going to be a little bit of a review, but if I standardize a variable, I turn it into a z-score. What should the mean of my z-scores be? I'm subtracting the mean from every single observation and dividing by the standard deviation. When I subtract the mean, my new mean should be 0. Standard normal distribution is centered around 0. So if I've done this correctly, hopefully, if I summarize, and I don't think I have this in the, well, I've got something else in there, but I'll do this for us now. Pax per capita. So I'm just kind of using that sum command, looking at that pax per capita standardized variable. Sure enough, I get a mean very, very close to 0. Now it's displaying the value to me, so even stata is going to be like a little bit off because it has to round it to something, but it's very almost exactly 0, right? Also, what should the variance? Well, I'm coming up with blanks on the other questions, but the variance of a standard normal distribution should be 1, right? So what is the variance of my standardized variable? Well, if a variance is 1, when I take the square root of the variance, that gives me the what? Standard deviation. So notice the square root of 1 would be 1. So these standardized variables, or essentially I've turned them into z-scores, should have mean 0, standard deviation, or variances of 1. So in standardized variables, by kind of creating new ones, where are we at on time? Got about 20 minutes left. Okay, so before I keep moving here, any other questions before you keep going ahead? Hopefully this isn't, I don't know, looking less scary. Well, we'll revisit this. We'll kind of go back to the slides if we have time today. Otherwise, it'll spill over a little bit into next class. There we go. So we're kind of moving away from stata, thinking now, okay, we can look at statistics, the descriptive statistics of one variable. But a lot of the time, especially in economics, we want to know the relationship between two variables, right? What's the causal relationship? So here I'm going to have two variables that have what we call a joint distribution, right? So maybe I have class size and math scores, right? So if I were wanting to look at the relationship between class sizes and math scores, I'm going to have two different variables, x and y. How do I calculate what we call the covariance between those two values? Well, I would want to take every single observation, take its value for the x variable, so take its class size, subtract the mean, then take that deviation of class size from its mean, multiply it by the deviation of the other variable, y, from its mean. I want to do that for every single observation and then add them all up. That's going to give me my covariance, right? So start with the first observation, go to the very last, look at the deviation of each variable from its mean, multiply those two by each other. That will give me my covariance, right? So what would my units be here? It's kind of weird. Well, if I've got class size is the number of students, a math test score is like the points I get in the test, I'm multiplying the units, my covariances have really weird units. Like here would be what, student points? That doesn't make any sense, right? So the sign of the covariance, let's see if I didn't put it up here. So the sign of this covariance is going to tell us something about the data. So if I had, right, how are we finding this covariance between two variables? So we'll notice here, so I was adding up x minus its mean for every single observation, y minus its mean for every single observation, right? So notice what's going to happen. If I have a student, and let's say the very first student has a test score. So remember, X here was, I think, test scores, or no, it was, I flip-flopped them. Doesn't really matter. Class size, and I think Y was the test score. If I had a student that was in a class size that was above the average, what's going to be true about the sign of this deviation? I'm in a class size that's above the mean. This deviation will be positive. What if they have a test score that's above the mean? This would be positive. Positive times a positive would be a positive. So anytime I have a student that is in a larger than average class and has a higher than average test score, well, that's evidence, that one observation is evidence that being in a larger class size actually tends to be associated with higher test performance. So that should be adding a positive value. That one observation was evidence that there was a positive relationship between these two variables. Now, if I go to the next observation, well, what if they have a below average class size and they had a below average test score? Negative times a negative is positive. What was this evidence of? When I saw this one observation, when I saw something that was below the average class size, that student also had a below average test score. That's evidence that there's also a positive relationship with these two things. When X is lower, Y tends to be lower. So there's a different way of saying that when X is higher, Y also tends to be higher. Okay. Now, some observations, I might see someone with below average class size, but an above average test score. This would actually give me a negative value that I would add in, because that one observation was evidence that, well, when class sizes are smaller, test scores tend to be higher. Now, I'm going to do this for every single observation and then add them all up. So if I end up with a covariance that's positive, what must have been true? That I had more students that had either, both the class size and test score on the same side of the mean than I did students who had class sizes and test scores on opposite sides. So that would be evidence that I've got a positive correlation, right, or a positive covariance, I should say, between these two variables. If I see that it's negative, it must have been that there was more students like this or like this, where these two variables tended to be on opposite sides of their means, which meant that when X was high, Y tended to be lower, or that there was a negative relationship between these two variables, okay? So the sign of our covariance kind of tells us, like, if we were to graph this out, what would a positive covariance look like? Upward sloping, if I'm thinking about the relationship between this X and Y variable. A negative covariance, what would that look like? Downward sloping, okay? So the sign of the covariance tells us that, I've got all of these students, and some of them are evidence that these two things tend to be on the same side of the mean. Some of them are evidence that they tend to be on opposite sides. But if the overall covariance is positive, that's telling me that there's more students where these two variables are on the same side of the mean, right? On average, these variables tend to be on the same side of the mean, or there's this positive correlation or positive covariance between them. What would a covariance of 0 mean? That the two variables are on average kind of, right? So I'm adding this up across multiple observations. So it would mean that every single time I have evidence of them being on the same side of the mean, I have equally number of observations that they're on opposite sides, which basically means that I have no real relationship on average between these two variables. Okay. Now, will it ever be exactly 0? Probably not, right? It's probably going to be either slightly positive or slightly negative. What else do I want to say here? I think that should be good. So we talked about the units. So the units are a problem because I might want to compare the covariance of, say, class size and math test scores to the covariance of, I don't know, the number of dollars given to the school and test scores, right? I might want to see, like, which one influences it more, which one has a stronger relationship. Well, they're going to have, the second example I would have, instead of student points, I would have dollar points. I can't compare things with different units. So one thing that we're going to do is take that covariance. If we divide it by the standard deviation of each variable, not only, so if I take, right, student points, divide it by students times points, it gets rid of my units. So the correlation will be a nice unitless measure if we take the covariance and divide it by the standard deviation of each variable. Also, and I won't go through like the formulas behind the scenes and like do all the math and cancel out. What this will always simplify down to, when we divide by the standard deviation of each variable, it's always going to give us a correlation coefficient that's between either -1 and 1. It scales it so that we then can compare across different data sets. So my correlation coefficient will be unitless, and -1 will be the strongest negative relationship between two variables, and +1 would be the strongest positive relationship between two variables. Okay. And if I saw a correlation coefficient of say 0.9 between two variables, I could say they have a stronger correlation than if I saw one that had 0.3. So the larger in magnitude that correlation coefficient, the stronger that relationship is between those two variables. Okay. So it allows us to kind of compare across. So I have that Excel file, which I will save for next class because I want to spend a little more time on that because there is a quiz question that's going to look kind of similar to that. So I've got a scatter plot here. This is kind of related to the covariance and the correlation coefficient. But if I wanted to create a scatter plot, and I'll show you how you can do this in Stata here before we get out today. So here it just plots every single observation that was in my data set. If I was trying to draw a line that best fit this data, would it be upward or downward sloping? You had to choose one of those two. If I'm trying to draw a line that kind of best fits this data, probably upward sloping, right? It might not always be clear, right, depending on the data set, but it looks like there's probably a positive relationship between math scores and class sizes, which means if we calculate the covariance, it should be positive. Yeah. So we looked at Stata here real quick, and we'll kind of come back to these slides here. I don't think we won't finish up exactly what's in the slides yet here today, but here we go. So here I can create scatter plots between any two variables. So I have here, I want to create a two-way scatter plot. So I have to just tell it two-way, and in parentheses, it's a scatter plot. So this is like what I showed you in the slides. I want to create one of those. I just want to take every observation and plot it. So I want to look at the relationship between the cost per pack of the cigarettes and the state tax. What should those two things be? State taxes are higher, pack of cigarettes are likely higher. Right? So these should be positively correlated. So if I go ahead and run this, it might take a second because it's creating a graph. It's thinking, oh, put it up over here. Sure enough, there's almost like a one-to-one, right? Because what's baked into the cost per pack, the state tax, right? So that shouldn't be that surprising. So we can create these scatter plots. Another command that we can think about looking at when we're talking about distributions is this hist command. So a hist command is kind of like the sum command. It's just instead of giving you the descriptive statistics, it's going to create a histogram for you and kind of show you what the distribution of that data looks like. So I just want to look at packs per capita. If I looked at the distribution of that, and it'll kind of force it into these bins. And there's a bunch of like different edits you can change and play around and make these graphs look really nice and pretty. I usually we're not going to mess around. It's just formatting and editing. So it's not really what this class is meant for. But we just want to kind of get like a rough idea of what does this distribution look like. Right? Looks like most packs per capita in most states are kind of centered around this 80 value. There's some states that have quite a bit lower, some states that have quite a bit higher. Just kind of give us a quick glimpse into what that variable looks like. If I do this hist command for that standardized variable, once again, what should it look like? It should have a mean of. So I said when we standardize a variable, it becomes a z-score, and the mean will be 0. We also said the variance will be 1, or the standard deviation will be 1. And when we standardize a variable, it should actually be symmetric. So if I click here, so we got some kind of weird thing going on in the tails, but it's pretty symmetric. Sure enough, it's centered around this mean of 0, which we saw earlier when we actually looked at the mean. But just showing that you can kind of look at the distribution of different variables if you want to. Okay. And if that's something I ask you to do, like on the first problem set, all you have to do is hist that, but you don't have to play around and make it look nice and pretty. Okay. All right, so we'll come back to conditional distributions next class, but I want to show you guys something before I let you go. Maybe. I broke the computer, hold on. There we go. So we will talk about the normal distribution next class. So we'll go through this. I was planning to go through it relatively quickly. We'll start to look at things like, I don't think I have it in the slides. Know that I put it up on here already. So we'll start looking at these Z and T tables. So did you guys didn't use Z or T tables in 370? Or are you just forgetting some of this stuff? But you've definitely heard of these tables before, right? Okay. Don't worry. We'll kind of use these to start thinking about how we build confidence intervals. Hopefully that's sounding familiar. How we do some hypothesis testing. Hopefully that's sounding familiar. Because we're going to start to see how we're going to start to do this in Stata as well. So I'm going to kind of review that standard normal student T distribution, review confidence intervals, review hypothesis testing, and then we'll see how do we do that in Stata next week. Okay. So some of the stuff that we didn't get through in the slides, I'll probably just copy and paste. So I never know how far we'll kind of get in that first week, especially given like Stata issues, like with helping other people and things. So I'll get up the next kind of week's slides. I did put up the first set of sample questions. The first quiz I'm not going to put out there yet because we haven't covered everything. I'll post that first quiz after class, likely next Thursday. We'll have covered all the material that you would need for it. But if you want to start thinking about some of the early things we've already talked about that might show up on that quiz, that's going to be in those sample questions. Okay. You may also see tomorrow me put up that first problem set. Once again, you might be able to kind of get a little bit of a start on it. The first couple questions, maybe things that we did today, start to kind of familiarize yourself with working with these data sets. But a lot of it's not going to be until things we cover next week. So don't feel like you should have like a lot of it done. I just want to get it out there early if you do want to start working on it. Okay. Other than that, next week also starts when I might take, if you could also fill out that background survey, and next week starts when I might be using these in-class quizzes sporadically or randomly. Okay. Also, I haven't got any questions from you, but I have 600 B251 students, and I got a couple of them asking. So I won't have office hours on Monday since it's Labor Day. I'll post an announcement. I'm just going to have extended office hours on Wednesday next week, but we will still have class on Tuesday, right? I know that some professors, if they teach the same class on different days, will cancel class. We will have class on Tuesday as regularly scheduled. Okay. Other than that, enjoy the weekend. We'll see you guys on Tuesday. It's all perfect. Thank you.